Welcome to another episode of Code for Thought. Quantum computing has stirred the imagination for a long time. It has been hailed as the dawn of a new age and as a new revolution in computing. Some of the hype is more fiction than science, though, as Oliver Brown from the University of Edinburgh will explain in a minute. I met with Oliver late 2022 to talk to him about quantum computing. Oliver is a Chancellor's Fellow at the University in Edinburgh in the UK and has been working in the Quantum Software Lab for some time. His work is part of the Edinburgh Parallel Computer Centre, or EPCC for short, where he leads the Quantum Applications Group. But before we go into the interview, there are a few shout-outs for forthcoming conferences in 2023 to make. First in the list is the annual conference of the Society of Research Software Engineering in the UK, and this year it will be held in Swansea between the 5th and the 7th of September. The event will be hybrid, and registrations are open now. Hot on the heels is the unconference of the German RSE community in the picturesque city of Jena between the 26th and the 28th of September. I believe the deadline for submissions has expired by now, but the registration should open soon. And then, of course, there is the US RSE conference in Chicago this year between the 16th and the 18th of October, and this will be the first US RSE conference ever, which is super exciting. In short, it will be a very eventful autumn indeed, and I'll be talking to some of the organizers, which will provide further info as we get closer to the event, so stay tuned. And now back to my conversation with Oliver Brown about quantum computing. Hello, Oliver. Welcome to the show. Thank you very much for your time. I know how busy you are. But before we start talking about quantum computing, maybe you can introduce yourself quickly.
Hello, and thank you for having me. So I'm Oliver Brown, and I'm an architect at the EPCC, although I like to say quantum software architect, which is a nice bit of marketing to help people understand what it is I actually do, which is work on quantum applications, particularly as they relate to high-performance computing, which is really EPCC's main area of work. And I've been here for over 4 years now, working on various things, particularly around heterogeneous computing, and more recently quantum.
Well, quantum computing is a big buzzword. Well, it's not so much a buzzword, it's actually real, but it's buzzword in the way it's being treated very often. So I want to disentangle that a little bit. But maybe we can start by clarifying what we actually mean by it. So we know the classical computer with bits and gates. So what does quantum computing bring to the table? And how is that different?
Well, so it's a good question, an important point. Quantum computing really takes us back to square one when it comes to computing. It's a completely different mathematical model right at the very bottom level of abstraction, at the level of a bit. So instead of a bit, now we have a quantum bit, or a qubit. Now, in many ways, a qubit looks a lot like a bit. It has two states, 0 and 1. The difference is that being a quantum system, all of the quantum laws that quantum mechanical systems follow apply, including the law of superposition, which means that any state, any arbitrary linear combination of 0 and 1 is also a perfectly valid state for our qubit. And perhaps more importantly, our qubit has a phase internally. Now, what I mean by that is, if we think of an example system in which you might implement a quantum bit, photons are a popular choice for communication applications because they travel extremely quickly. Light travels as a wave. We know that hopefully from our school physics. However, when we look at quantum mechanics, we also say that at the same time as being a wave, it is also a particle. However, it is a particle with wave-like properties, including a phase, a particular alignment of the wave as it travels. And if you have two waves that cross each other or overlap at a point where they're both going up, then you get what's called constructive interference, and the size of the wave doubles. However, the opposite can happen when they overlap at a point where one is going up and the other is going down, and you get destructive interference, and you get nothing. Your light is destroyed. So qubits have this property too, and that means they have an internal phase which needs to be recorded with regard to themselves. So that means when we're describing the state of a quantum bit, it's no longer a case of having a 0 or 1 for every bit. Instead, we need to track a complex number for every possible collective state of our quantum system. So if I have 3 qubits, Then I need a complex number that describes the amplitude and phase of the 0, 0, 0 state, and so on, all the way up to 1, 1, 1. So I need 8 numbers. And this is our first big sort of problem with quantum computing, is the scaling problem. We need an exponential number of numbers, of complex numbers, to describe the full state of a quantum system. So we have to keep track of this phase information as well. And all that's really important because it's that quantumness of the bit of the model of information that we have that also gives quantum computing its power. Classically, as you mentioned earlier, we have gates and bits. In quantum computing, we still have gates and we have qubits. But there are a few more gates that can do some sort of interesting quantum-only operations. And because we've changed that low-level abstraction, everything else we've built on top, including data types and all that stuff that we're familiar with as software engineers, perhaps, that all goes out the window too. And we need to start again with assembly, basically.
Okay, which I guess makes it very interesting. But sort of the bits, the qubits they look similar to bits, but obviously they have very different behavior because of the superposition,
Yep.
the wave-like behavior of particles in quantum physics.
Yes, indeed. And as I say, it's that's particularly important. And the reason I say that is because if we just had superposition, if we just said, okay, it can be a linear combination, but we didn't have this phase and this interference properties, well, then we just have a model of analog computing effectively. We tried that before. We already looked at ternary and quaternary systems and even completely analog computing systems, find ourselves coming back to binary digital systems instead as the most efficient way to do computing in general. That property, the superposition property, although it is often the first thing that people talk about when they talk about quantum, it's not, from a computing perspective, it's nothing. But the point is actually that these collective states, where they interfere with one another, that leads to a set of uniquely quantum computational states, which we describe as the entangled states. And these states cannot be separated. What I mean by that is I can't describe them as a simple product of the individual states of each qubit, but instead I need a specific description for those collective states that are entangled. And that, again, is why we have this scaling problem, because we have these non-separable states that we need to be able to describe.
And that, of course, is a particular characteristics of quantum physics, because in classical systems you don't have that. And just for clarifying, I mean, we're talking about quantum computing. We're not talking about a box. We're actually talking about the abstract way of computing, just to make that clear, because we come to the practical aspects of quantum computing, hopefully a little bit later.
Yeah, absolutely. This is all very much at the kind of information theory level of things.
Indeed. So the other aspect is gates. So we have the qubits with all the very different behavior than we would normally have. And then we have gates. So what kind of gates are known, and how would you explain that to people? What they actually are and how they behave?
In many ways, there's a lot of gates that look very familiar to people familiar with classical electronics. You have a NOT gate, for example. It just flips from 0 to 1 or 1 to 0. You can build analogs of the standard AND, OR, NOR, XOR, and so on. Nothing particularly exciting there, but all those things are still perfectly feasible in quantum computing. Obviously, this understanding what the output state is going to be is a little bit more complicated, because your input is not 0 or 1, it's maybe 0 and 1. So, what does that mean? But conceptually, you find that the maths all just sort of falls out and you get something that looks roughly the same, and maybe the output is a little bit more complicated, but you can figure it out. Perhaps the more interesting ones are the quantum-only gates. And the big example of this is the Hadamard gate, which is effectively a superposition gate. So it takes the state 0 to the state 0 plus 1. And that's where you start to see the kind of more exciting things. And also in gates that span multiple qubits. A lot of quantum circuits and algorithms rely on controlled gates, for example. Now, a controlled gate classically is not that exciting. Okay, the control bit is 1, then a thing happens, and if the control bit is 0 and it doesn't. But again, what happens that makes it more interesting is what if I put a superposition into that control state, then what's the output going to be? It tends to be, though, ultimately all these things boil down to, it makes all the maths of what your output's going to be a lot more complicated. And a little bit harder to follow, I'm afraid.
Indeed. I mean, as you say, in classical computing, that's quite simple control gate because it's on or off, but then you have on and off and everything in between.
And the answer is if your control bit is in a superposition, well, then your output ends up in a bit of a superposition as well. It's precisely the superposition dependent on the control gates. The result is if it was 0 and the result if it was 1. And it's those kind of operations that let you build up entanglement in your circuit. and therefore let you access these important quantum states that are purely quantum and not classical. And those are the ones that really give us any power from quantum computing.
Yeah, maybe we can talk about entanglement a little bit later, because I think there was a Nobel Prize this year for that kind of work, which is often described as the second revolution in quantum physics. Before we do that, when you study quantum physics, you learn that conducting an experiment influences the system being tested, and I think that's known as quantum decoherence. What does it mean for quantum computing, and is there anything that can be done about it, or what would you do with it?
Well, so that's a very good question. And there's actually two aspects, I think, to the measurement problem, one of which is a problem and one of which is not. There's measurements that we do that we want to do. That's how we get our output from a quantum computer at the end, right, is we do a measurement on qubits. And one thing to know about that is that when you measure a qubit, you only get one bit of data out of it. Because the answer is always 0 or 1. And computers are not generally set up in a way that they can perform measurements in different bases. So we rely on strictly getting output data in a computational basis. It looks like a classical bit string. And that's good because, we couldn't possibly store all of the quantum information on a classical computer, so we need to be able to reduce it to some kind of classical output at the end anyway. But the downside is it means that for many of our algorithms, we may have to run the experiment multiple times in order to build up a statistical picture of what the output looks like. But that depends entirely on your algorithm. But certainly there's a point where we always want to do a measurement. And sometimes there are algorithms where you have ancillary qubits that may be used to perform measurements as well after entangling with other ones. And that can be part of the actual algorithm process even. We have algorithms that rely on you doing these kind of measurements to reduce stuff. It can also help us with simulation. When we do a full state vector simulation, which is when I simulate every amplitude, every complex number for every possible quantum state, in a sense, I'm doing more work with my classical computer than with the quantum one. At the end of that, I end up with a state vector representation, whereas from my actual quantum computer, what I get is a classical bit string that I've measured. So we can use measurements to reduce the amount of computational work that we have to do using more sophisticated simulation techniques. And that is all great. The flip side of that is exactly as you say, the kind of decoherence problem, which is not when we're performing a measurement, but we often think of that as something like the environment performing a measurement. And in fact, this is my PhD. It was in this area. I was working on open quantum systems. Now, I admit in that, what we did is generated a very particular environment that precisely matched the properties that we needed it to have in order to make our experiment work. Which is quite a common approach in open quantum systems, simply because you need to do something to make the problem tractable. You can't possibly simulate both your quantum system, which is of a certain size, and some arbitrarily large environment it's connected to. You need to do something. And often you'll do something that will make it so that your smaller system is also easier to simulate. In terms of practical quantum computing, the real issue is that because of this interaction with the environment, basically qubits aren't very stable. Now, your laptop, my laptop, generally speaking, they work perfectly well, right? So much so that we don't do any kind of error correction on standard domestic electronic memory. On something like a server or a supercomputer like Archer 2, that's different. We do use error correcting code memory, ECC RAM. Basically, the way that it does error correction is by having redundancy built in. So you have check bits that confirm that things haven't changed when they shouldn't have. So we'd do the same thing for quantum computers, right, if we had enough qubits to do so. But we do need to do something because the level of instability of qubits is much, 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 much higher than in classical bits. As an example, there is a Chinese quantum computer called Zhuqiangji. But importantly, they actually published in the paper on their quantum computer the error rates of applying gates or 2-qubit gates. And there is a difference between applying 2-qubit and single-qubit gates. Basically, single-qubit gates are easier and less error-prone. But it was something like on the order of 1,500 or so single-qubit gates before an error, and about half that for the 2-qubit gates. To give you some context of how many gates, a really popular algorithm that we'd love to be able to run is quantum Fourier transform. And that requires n squared minus n gates, where we have n qubits. So it does not take long at all to get to a point where the depth of your circuit, the number of gates you need to apply, is far larger than you can apply without creating an error in your system. By analogy to classical computing, classical computer is doing 10 to the 9 operations a second. So that's a second's worth of classical computing, less than that even, far less than that, before you hit an error where you'd never use a computer. It's not quite straightforward in the sense that, a quantum computer, in theory, has this powerful computational ability that means a qubit, from a computing point of view, not from a data point of view. As I mentioned earlier, one qubit is worth one bit of data when you measure it, and there's no getting around that fact. But in terms of computing, you can do a lot more with a quantum bit than you can do with a bit. But even so, it's not so much more powerful that we can get away with just running 1,500 gates and do anything really useful. Quantum computing, as you mentioned, is a bit buzzwordy and there's a lot of hype around it. And I think one of the most important parts of my job actually is kind of expectation management.
Which I hope we're going to do here in this episode.
People are totally understandably really excited about quantum computing. I get it. I love quantum computing. But I would even regard myself, in comparison to some people, as a bit of a quantum computing skeptic. My view is that it may well be useful, and now is a great time to find out where. But there's no, I think, concrete evidence yet that it actually will be useful. We at least have a lot of theoretical evidence that it should be. But, there's a big gap between the algorithmic speedup that we can see and actual speedup, particularly when a quantum computer maybe operates at megahertz repetition rates versus gigahertz for a classical computer. There's a big gap there to make up for in terms of what you're actually achieving. Now, there are also, performance isn't everything. There are some problems that we may be able to solve on a quantum computer that we simply cannot on a classical one. So that's another big selling point. And that's the reason everybody is really interested in it. And so much effort has gone into building quantum computers that do function. And they do. I can't take away from the achievements of all the hardware groups in particular who've really made functional quantum computers, which is in itself a massive achievement. And in particular, people talk a lot about the Google Quantum Advantage paper from a few years back now. Their achievement, again, is absolutely huge, especially on the hardware side, and all of the control electronics and stuff to make all that work with a superconducting qubit system is amazing. And I'm really glad to see it happening and hope to see it continuing to scale. People are making much bigger quantum computers now. IBM are talking about their 128.
I was about to mention IBM, yeah. I think we're jumping ahead a little bit. I think we're now coming to the practical aspects, but I think there still is a more theoretical side that I think we might want to talk a little bit about, which is the algorithmic side. So you already mentioned that. We talked about qubits and how they're different to classical bits. We talked about that at the end, the output actually the data points will still be sort of classical zeros and ones. But what about the algorithms? And what kind of algorithms are there at the moment, and how are they different, or how do they have to be different?
The first thing about writing a quantum algorithm is that it's significantly harder, I think, than a classical one, simply because the mathematical model is completely different. You have to adjust your brain almost to think in a way that a quantum computer operates. And we're still writing these algorithms and designing things precisely at the level of gates. And some register of quantum bits. Another big physical law that we have to follow with quantum computing is the no cloning theorem. And that says we cannot copy quantum data. So there's no concept of I'm going to do something with my quantum state and then just stash it over here and then come back to it later.
That's a shame, because we have the Heisenberg compensator from Star Trek, don't we? That doesn't quite work then, does it?
Yeah, indeed. I wish. Absolutely. So, that's a really significant challenge, actually, from the point of view of developing quantum algorithms, because you're basically stuck with a completely imperative programming model, right? Where you have your register that you transform using gates, and that's it. Because so much of quantum computing relies on collective states as well, you need to think in terms of the whole register being transformed, not just individual bits. Ultimately, what it means is we've kind of been funneled down a fairly narrow set at the moment of quantum kernels that do certain limited operations, however, that have been proven to be mathematically useful. So what I mean by that is there's a set of algorithms called the oracle algorithms that I think are less practically important, because they're the kind of things where you say, okay, I have a black box that can do this for me, and then what could I do with a quantum computer around that? But they're interesting from an information theory point of view and from a very theoretical perspective, but probably less functionally applicable in the real world. At the other end of the spectrum, we have the quantum Fourier transform, which is the kind of golden child of quantum computing. And really all a quantum Fourier transform does, it's not quite the same thing as a traditional discrete Fourier transform, because it does a Fourier transform of the quantum state. But what that does is provides us a way of doing period finding of a function through various means. That's its most important application so far anyway. But generally, the QFT is the one that everybody wants to use in their algorithm, because it will generally lead to exponential speedups, because it is so much faster at doing the thing that it needs to do. And in between, you have Grover search type algorithms, which use a different approach, and that gives you maybe polynomial speedup. We basically look for ways to apply these things, right, is what it boils down to.
So let's talk a little bit about the practical aspects of quantum computing now that we talked about entanglement, etc. So you already mentioned Google and IBM and other companies that have built computers that could be described as quantum computers. So where are we actually now these days with practical implementations?
We are in what is known as the Noisy Intermediate Scale Quantum Era, or NISQ era. And what that means is we have a quantum computer, a real-life functional quantum computer that is far larger than anyone can simulate classically, but not large enough that we can start to group together multiple physical qubits into single logical qubits and thus implement error-correcting codes. We're not at a stage where I can go and implement whatever algorithm I want because I know I've got some number of error-corrected logical qubits to play with. But we are at a stage where the machines are bigger than we can simulate, certainly exactly, right? I can't do an exact simulation of any quantum system. In my case, above 44 qubits or so. Now, you can get much further using approximate techniques, but for the state vector simulation, because of the 2 to the n size of the state vector, and it's 2 to the n times 16 bytes, so you quite rapidly get to large amounts of memory doing that. So, for example, using 512 nodes of Archer 2, I was able to simulate quite comfortably 42 qubits, but I would need 1,024 nodes to do 43. So anything sort of above that mid to low 40s range is basically beyond my reach, and quantum computers out there exist and are that large. Drawback, as I kind of mentioned earlier, is the fact that you can only apply so many gates before you hit an error, and once you hit an error, you're pretty much doomed. Now, you can do many repetitions to try and average to the correct result, but at a certain depth, it simply becomes impossible. And the problem is that the number of qubits that we have, maybe next year 128, but in the classical world, we're used to 64-bit data types. So, what can you encode in 128 qubits? In some sense, a lot more than you can encode in 128 bits. But you have to remember that you can still only get 128 bits of information out the end. So if your solution doesn't look like a classical bit string, then you're already sort of in trouble there. Quite often it needs to look like a probabilistic distribution of 128 bits, because with some probability you'll get the particular answer out of your quantum computer. So you just repeat the experiment multiple times. Now, all these things are completely reasonable limitations of quantum computing, but it means you end up adding multiple asterisks, multiple caveats whenever you start talking about the power of quantum computing, because there's a big gap, I think, still between the theoretical algorithmic speed up and the promise, the carrot that's there, and intractable problems becoming tractable, and what you can really achieve. And I think there's a lot of work to be done in that direction. That's one of the things that we're particularly focused on here at EPCC, is trying to figure out where are the kind of mid to near term best places to target our efforts in quantum computing, and how are we going to get them to interact with our classical computers. And they do need to interact with a classical computer. It's worth saying that as well. Anyone who tells you that in the future we're just going to be using quantum computers is talking complete rubbish.
I shouldn't get rid of my laptop just now, then, shall I?
Absolutely not, no. And the reason, the simplest way to explain why they're not really serious is that this thing about no cloning theorem, not being able to copy data. Imagine how many operations that your computer does every day that rely very much on its ability to copy data around multiple times. You cannot do that. And that's not a short-term engineering limitation. That's a physical law that we are butted right up against with a quantum computer. There's plenty of things that are far more efficient on a classical computer than they ever will be on a quantum one.
At least from our perspective now.
Indeed. Even in the future, I think, you can implement a completely classical computation on a quantum computer, but why would you? Why on earth would you ever think that's a good idea? Given all the engineering challenges, but also, let's say, some of the physical limitations, it just makes a lot more sense to simply keep your classical stuff on a classical computer and then call out to the quantum computer for those algorithms and those functions where it really can make an exponential difference and get that data back.
You mentioned medium to short-term goals. So from your perspective, what would they be?
Well, so as I mentioned earlier, combinatoric problems we like because the output naturally maps to a classical bit string, so it's very simple. The real answer that encapsulates everything, to be honest with you, is anything that looks like a physics problem already. So, quantum physics is obviously a target, and that then extends to things like chemistry.
Are we talking about simulations, chemistry?
Exactly.
Okay.
Of quantum systems. And indeed, a lot of the kind of popular near-term algorithms, so the most popular one is variational quantum eigensolving. Now, it's a near-term algorithm because what we've actually done is moved a lot of the computational complexity out to the classical part. What it does is sets up a circuit and then varies the parameters of that circuit at each iteration. But it does that using a classical optimizer sitting on the outside. Now, the problem, of course, is that you end up with an exponential scaling in the number of gates that you need to optimize classically, and that in itself ends up being the bottleneck. But the point is that this is a way of targeting a quantum problem using a quantum computer that we can do right now with a very limited number of qubits and a very limited number of gates. So those are the kind of near-term targets, the things that already look like quantum physics problems. Longer term, we start to look at more abstract application of the various algorithms that we can concoct for a quantum computer. But the real dark art at the moment, the magic of using a quantum computer successfully, is precisely in that step of mapping your classical problem onto a quantum computer in some way that you're not bothered by the fact that you get a classical bit string out the end, and that you're not relying on putting a lot of data into the quantum computer, which isn't really something, it's not a road you want to go down if you have to precisely prepare a bunch of qubits. Generally speaking, you want a sort of arbitrary initial state, and then you do something to it via a series of gates, and you may iterate those gates and you may change what they are based on some classical computation outside, and then you want a bit string on the output. That's the ideal for how a quantum computer will operate.
That would lend itself for simulations. It also potentially, and that's why it's been mentioned several times, cryptography, so they say. Do you have a view on that?
I do. So, as I mentioned earlier, one thing the quantum Fourier transform has been shown to be tremendously useful for in theory is period finding. As it happens, there is an algorithm that Peter Shor concocted for finding the prime factors of large semi-prime numbers that uses period finding at its core. Well, in fact, I don't think Peter Shor came up with that. I think Euler came up with that. And Peter Shor showed how you could do it with a quantum computer.
Yeah, that's the Shor algorithm then.
Yes, indeed. And now finding the prime factors of a large semi-prime number is a tremendously tedious and utterly dull application, except for one thing, and that is it just happens to be the one-way function that Rivest, Shamir, and Adleman chose for their RSA cryptography, upon which all security in the digital world has relied for the last sort of 40 or so years. This immediately tends to cause panic, and the sorts of, everyone worrying that the quantum computer is going to come along and break everything. So first of all, let me assure everybody out there that it's not the case. And the reason it's not the case, as I already mentioned, quantum computers are pretty rubbish right now. QFT in particular relies on n squared minus n gates to be applied, and we don't have a quantum computer that can get anywhere near that for any reasonable size n. So the number of qubits you need is on the order of the number of bits in the large number that you're solving. It's not a near-term algorithm that you could apply. It's very much a long-term thing. And we already have come up with what we hope are quantum-proof encryption methods. And these are actually already there in, say, the latest version of OpenSSH, for example. Cryptography is sort of way ahead of the game. So that's the good news. Security is not really at risk from quantum computers because we know that there would be a problem if we weren't aware of it. But yeah, absolutely. It's the kind of killer application of quantum computing, or was for a long time, was this. And the reason for that is because it's a very computationally challenging problem, but it's one where you can get an exponential speed up in the algorithm. That is a huge carrot for anyone out there looking at computers.
So when we talk about the physical implementations of quantum computing, could you give us a quick overview, quick being relative probably, of what's actually out there?
One of the key things is it's not like our classical computers. Our laptops in the sort of mid-1980s, everybody converged around CMOS transistors and never looked back. Classical computers have had the same fundamental representation of a bit physically for many, many years. Quantum computers are still very much at the anything goes phase, where there are multiple competing technologies, all with their own set of advantages and disadvantages. In the communications realm, that's pretty much entirely photonic. There's another cryptography application, really. The big one there is quantum key distribution, whereby you are able to share an encryption key and importantly, you know whether or not anyone has intercepted it by measuring the error rate at the other end, right? You can't do anything if it has been intercepted other than decide not to send a message.
Just knowing that it has been, yeah.
Exactly. So you know whether or not your cryptography key is secure or not. There, it's all optical, and optical is really the king, as I mentioned earlier, whenever communication is involved. There are bosonic sampling devices for quantum computation using photons, but the process is trickier because photons fundamentally move from point A to point B, and at point B they're absorbed and gone, which makes it challenging to do anything much with them in between. The more popular computation implementation is something called a superconducting qubit. This is what Google are using and IBM are using. And those are the big, if you've ever seen, it looks like a big gold chandelier. That's a dilution fridge in which these things have to live. And actually, that's the biggest part of their energy usage then, is just cooling. And the challenge is getting your control circuits in and out without heating it up too much, basically. The way that they're controlled then is with radio frequency signals, which is something that electrical engineers and computer scientists understand well. So we really like it from that perspective. And the actual qubit itself is it's called a Josephson junction. And fundamentally, it is a couple of electrons spinning around a superconducting circuit. And the direction that those electrons travel is broadly your 1 and 0. So that is the fundamental implementation for a lot of systems in this. They can be controlled with these microwave radio frequency circuits. Now, the other options that are less popular but are out there tend to be trapped ions and even trapped neutral atoms. So these are trapped ions are ions trapped by a laser in a particular location. And basically, it's the number of ions that you do or don't have in there is your 0 or 1 in each sort of site. IonQ, for example, is a company that makes these. And what's nice about them is they can be room temperature. The other one is neutral atom, which is similar to the trapped ion things, but it's a little bit more challenging to get neutral atoms to interact. And really, that's the big difference, right, between each of them. Some have much better coherency, much better lifetimes for how long the state will live. The price you pay for that is that it's much harder to make them interact with anything at all, including the gates that you're trying to apply. Typically, a gate, the way that works is for any of the kind of trapped something, that's a laser, a particular laser pulse gets applied. For the superconducting ones, a similar approach in that it's a particular control frequency. And then for the optical ones, a gate is really a photonic crystal or a filter or a polarizer, anything like that. You do get electronically controlled optics, so it is doable to kind of do that on the fly, but the traditional approach actually was just to set up a circuit and it would be built on an optical table.
I mean, it's a huge subject to talk about, and we're really barely touching the tip of the iceberg here. But for those of us who want to get into it, what would you recommend? I mean, where would you start? I mean, you probably would need to have some background on quantum physics. Or do you? Can you actually, for somebody who's not a physicist and didn't study that, could they get into that?
You know, I can't argue with the idea that it's helpful. And I forget, I did my undergrad in physics at Heriot-Watt, and then I did a PhD there. And in that time, I've forgotten all the things that I know that not everybody knows. Every year, I suggest an MSc project around quantum computing. And every year I forget quite how much work a student is going to have to do because it changes the mathematical model. Earlier on, we touched on the Nobel Prize winners in the second revolution in quantum sciences. The reason it's called that is partially because it's really at the level of what we call second quantization, where we look at information theory view of quantum physics. It's relatively simple in this for someone to jump in without any background in quantum physics. Looking at like black body radiation, all that stuff is nowhere to be seen. You simply start with bras and kets, which are these kind of triangle bracket things. And they're 0 or 1, and they're represented as vectors, and then gates are matrices, and you're applying gates to these states. All the maths can be done at that level, but you do have to be willing to put the time in to understand that. There's no way around that, unfortunately, because there aren't the higher level abstractions yet that we have for computing that let us write some code in Python rather than doing electronics and putting together some NAND gates. But if you're interested in getting into this and you're not put off already by all the things I said, so there's a sort of standard textbook in the field called Nielsen and Chuang, Introduction to Quantum Computing, and that is a great place to start if you like a textbook. If you'd rather just work through some stuff online, then you can look at the Qiskit, Qiskit material. They have their own kind of handbook and some videos and a library for simulating quantum computers classically, which you can then use to put together your own circuits and see how that works and try some of their examples and tutorials. I think a background in quantum physics is not needed.
But a mathematical, you need to have some kind of mathematical understanding.
Because it is all very much at the level of doing some linear algebra at the moment, unfortunately.
Well, thanks very much, Oliver. That was very interesting. And I wish you all the best for the future.
Thank you. You too.
Oh, time's up. See you next time. But before I forget, this podcast is covered by the Creative Commons license. See ya.